Hi everyone, welcome to section 3.10, linear approximations. In this section, we cover two things, linearization and differential. Number one, linearization. A linearization of a function at a point is, hopefully you can tell, linear, just a straight line. So for a function, it is the function fx at this point A, fa. We have this straight line right here. Well, there is the tangent line. The equation of a tangent line is the linearization of the function at a particular number. Application. First example, approximate root of 3.98. fx equal root x is the function. And we also know that root of 3.98 is near root of 4, which is 2. So in this case, we're gonna need to find an approximation of square root x at x equal 4, or a linearization of fx equal root x at x equal 4. And then we know linearization is just equation of tangent line. For equation of tangent line, you have to figure out two things here. The slope and the equation. Slope is f prime of 4. So we know fx equal root x. This tells us that f prime x is 1 over 2 root x. So this 1 over 2 root 4, 1 over 4. Y minus y1 equal m, x minus x1 is the equation of a tangent line. Y minus y sub 1 is f of 4. Slope f prime 4, x minus 4. So y minus f4 is root 4, 1 over 4, x minus 4. So we have y minus 2 equal 1, 4, x minus 1. And y is equal to 1 over 4x plus 1. fx is approximately 1, 4, x plus 1 for number nearby x equal 4. Root of 3.98 equal f of 3.98, and this is approximately 1, 4 times 3.98 plus 1, and we have 0.995 plus 1, which is 1.995. Yeah, it is pretty cool because we can actually take a look at the actual value of root 3.98 Here come the actual value. Root of 3.98 using a calculator is 1.994993734. Approximation come out to be pretty good. Let's do another example. Second example, find a linearization of fx equal e to the x squared ln root x to approximate f of 1.02. Wow. Linearization, equation of tangent line. The first thing we do here is to figure the f prime x is using the product rule. So ex squared multiplied to the derivative of ln root x plus ln root x multiplied to the derivative of e to the power x squared. Ex squared times 1 over 2 x plus ln root x times ex squared times 2x. Use the chain rule. And we don't have to simplify this because the derivative is useful to figure out the slope. The slope is m equal to f prime of, to approximate f of 1.02, we're going to use a number nearby. And a number nearby 1.02 is 1. So we need to figure out the equation of the tangent line at x equal 1. Slope is f prime 1, which is e to the 1 square times 1 over 2 times 1 plus ln root 1 times e to the 1 square times 2 times 1. Well, ln of 1 is 0, which tells us that we have e over 2 as the slope. So let's figure out the y sub 1 here. Right? It's just f of 1. E 1 square ln root 1. Well, ln 1 is 0, so it's 0. Well, equation of tangent line is y minus y1 equal m x minus x1. Y minus 0 is equal to e over 2 x minus 1. So y is e over 2x minus e over 2. Pretty slick. And therefore, fx is approximately e over 2x minus e over 2 for number near x equal 1. So now we can figure out f of 1.02. And that would be approximately e over 2 times 1.02 minus e over 2, which is 0.51 e minus 0.5 e, half of 0.5. Subtract them, we have a 0.01 e. Very nice. One more example. Use Desmos to determine the interval on which the approximation root x plus 3 is approximately 14x plus 74 is accurate within 0.1. The square root is the function. The approximation is the linearization. And from here, we can cook up an inequality. So in order for the approximation to be accurate within 0.01, the absolute value of fx minus this linear relation has to be less than or equal to 0.1. We have an absolute value of root x plus 3 minus 14x plus 74 less than or equal to 0.1. And we can drop the absolute value to make it between negative 0.1 and 0.1. So root x plus 3 is between negative 0.1 plus 1/4 x plus 74 and 0.1 plus 1/4 x plus 74. Yay! So now there are 3 graphs that we have to do on Desmos. So this graph 1, graph 2, and this one. The function is the graph number 3. The intersection between those graphs will give us the interval. Negative 0.1 plus 14x plus 74. Okay, straight line. Second one, 0.1 plus 1/4 x plus 7/4. Oh, they don't intersect each other. They have a same slope but different y-intercept. Now, let's take a look at the function. Fx equal to root of x plus 3. Notice that the function intersect at these 2 points. So that means the interval is between negative 1.13 and 3.93. Differential. Differential is a pretty cool application of a linear approximation because we use it in real life. Now, think up. Delta x, say delta x as a small change in x. Then delta y would be fx plus a small change in x minus fx. Well, if delta x is small, and it's really small, if delta x is very small, then delta x is approximately dx and delta y is approximately dy. The dx and dy, we call them differential. And we can quickly get them by looking at the function y equal fx. Now take the derivative of both sides with respect to x. We have dy over dx equal to f prime x. So dy is f prime x dx. Application. Example 1. The radius of a sphere was measured and found to be 21 centimeter with a possible error in measurement of at most 0.5 centimeter. What is the maximum error in using this value of the radius to compute the volume of the sphere? So what is asking here is, what would be a dv equal to? We are given a possible error in measurement of the radius. So that is the dr, 0.05. Well, that is the sphere. The volume of the sphere is 4/3 pi r cube. So differentiate both sides with respect to the radius. We have dv equal to 4/3 pi times 3r squared dr. Now we can do the substitution. We have dv equal to 4 pi. Radius is 21 centimeter. 21 square. And dr is 0.05. That's small change. And then that is it. This is dv right here. Got it. Pretty cool. Next example, number 2. Estimate the amount of pen needed to apply a quarter pen 0.05 centimeter thick to a hemispherical dome of diameter 50 meters. We can relate the volume to the radius, but not the diameter. So here, the radius is half of 50, just 25 meters. The dr, 0.05 centimeter. Well, the unit of the radius is in meter, so we have to convert it to meter. Just 0.0005 meter. And now, just be careful, right? It's the hemispherical dome. So volume is half of the volume of the sphere, half of 4/3 pi r cube, which is 2/3 pi r cube. And then we differentiate both sides with respect to r. To get dv over dr equal to 2/3 pi times 3r squared. And now dv is 2 pi r squared times dr. The amount of pen is dv. Because when we pen around the hemispherical dome, we are changing the volume. dv is 2 pi, radius is 25 square, and for the dr is 0.0005. And that is it. That is the amount of pen needed. You can use the calculator to get an actual number. Thank you for watching. I hope you find the content useful. Please like and subscribe to help the channel grow. I will see you in the next video.